So good evening, everybody. So we are going to start the class. So like I told you yesterday, so this class is going to be a lab. We are going to do a lab-based class exercise. So I want you to go to to Modo. So in Modo, you are going to see I uploaded the Google Colab for today's exercise. So the Google Colab for today's exercise is this. Please keep quiet, everybody. So this is the exercise. So if you click this link, it's going to take you to the lab exercise that we are going to do for today. Okay, please keep quiet, everybody. Please keep quiet, please. So before we start today's lab exercise, so I will still come back to the exercise, but I just said it because of you, so that you start opening it, so that maybe by the time I'm done, then it's already be opened in your computer. So just a few things. So the video I uploaded for this particular lecture, it wasn't clear. So the video and the audio were not rhyming together, so it created some problems. So I will just quickly go over it for a few minutes. Then before I continue, there was in the last class there was actually a mistake I made for the mean square error. So the first equation I gave is the correct one. So the second one that I changed to, I said you divide by 2. That one is wrong. So the original one is, yes, the original one is the correct one. So please try to correct it in your notebook. So the original equation I gave as the equation for mean squared error, that is the right equation. So I just quickly want to go over this. So we are talking about tensors. So because we are working with PyTorch, we'll be talking about tensors. So tensors are simply arrays. So we have 3 levels or several levels of tensor. So first off, before we really deal with what is a tensor, we need to know the difference between a scalar, a vector, a matrix, then a tensor. So a scalar is just a single value. So it's just one value. But a vector, you all know a vector, like a collection of values on a single row. Then for a matrix, when it's 2-dimensional, when the collection of values is 2-dimensional, that's a matrix. Then for a tensor is anything from 3 dimension and above. So in PyTorch, the way you define scalar, vector, matrix, and of course tensor is quite the same, is kind of similar. So for instance, if you want to define a scalar, so you just put touch.tensor, then you write the name of the scalar. Then if it's a vector, it's still the same thing, touch.tensor. But since a vector is like a collection of scalars, then you put the vector inside. Then for a matrix, is pretty much the same thing. So a matrix is two-dimensional. So you have the first row here, which is a square bracket. Then the second row is also a square bracket. Then all of it, they are enclosed in a square bracket. So that's how you define a matrix in PyTorch. So tensor is so anything from one dimensional, because if you look at the Python code, even for scalars, we are still calling the torch tensor method for it. So anything from vector, matrix, then that's 1D, 2D, then 3D, they are referred to as tensor. Then there is like a similarity between the tensor and the NumPy array. So basically, maybe those of you that are familiar with Python programming, you might be used to NumPy array. So NumPy array is like the same thing, almost similar to tensor, and it's just that there are two different libraries from two different APIs or from two different deep learning framework. So, but if you want to, it is very easy to convert from a tensor to a NumPy and from a NumPy to a tensor. So this is the command you use. So if you want to convert this vector, which was defined as a tensor, to a NumPy array, so you use this .numpy command. Then if you want to convert from a NumPy back to a tensor, you just use the torch as .tensor, then you put the NumPy array inside. Then we'll talk about reshaping tensors. So this concept is really very important, especially in deep learning. So for instance, if you have this matrix and if you have this matrix and this is a 2 by 3 and this is a 1, it just has one row. So we normally reshape tensors because it is when we are doing deep learning, when we get to convolutional neural network, we'll see a point where we have to reshape the tensor. So we are going to we normally reshape tensors. So the command that you use when you want to reshape tensors, the Python command is, for instance, this is the tensor you've defined, which is a 2 by 3 tensor. Then you want to reshape it to a 1 by 6. Then you just call this .view command, then how you want to reshape it. So you want it to be 1 row and 6 columns. So we talk about this. So there is a difference between contiguous tensors and non-contiguous tensors, so which we are going to be discussing later. So all of these commands, you can just read it. So they are pretty much straightforward. When you just, because in Jupyter Notebook, like I wrote this as in text form, and this is the Python code. So you can just read it. Then when you read it, you understand what I'm doing or what we are doing in the Python code. Then there is something called contiguous tensor. So contiguous tensors are those tensors that each value in the array, for instance, each row. So what are contiguous tensors? Contiguous tensors are those that the values in a single row, they are stored next to each other in the RAM. So if you look at this tensor, look at this, and look at this. So they are next to each other. So all the elements in a row are next to each other in the RAM. So if you look at this row, all the elements are next to each other in the RAM. But if mistakenly we transpose this tensor, so when you transpose it, the rows becomes the column and the column becomes the row. So if you transpose this tensor and it becomes this, it becomes non-contiguous. So why is it non-contiguous? The row like this and this is supposed to be next to each other in the RAM. But if you look at this and this, they are not next to each other in the memory. Also look at this. So that's what we call non-contiguous tensors. So it is possible to determine if a tensor is contiguous or not by just using the dot contiguous method. Then there's a way you can force the tensor to be contiguous. So for instance, this is the original tensor, but when we transposed it, it now became non-contiguous. So in order to force it to become contiguous, you have to use this contiguous function. So when you use this contiguous function in the memory, another memory space is going to be created such that the values in each row of the tensor, it is next to each other in the memory. So that's what we call contiguous. That's how you force it to become contiguous. Then we have something called named tensors. So named tensors, we introduce the concept of named tensors to avoid the problem that comes with broadcasting. So what is broadcasting? For instance, if you have this array, this numpy array, so like I said, a numpy array is also the same thing as a tensor. You can easily change it. So, and if you want to multiply this by this, you know that this is a scalar and this is a vector. So originally, if you do the multiplication, you are going to get this. And that's because of the concept of broadcasting. So automatically, the Python would be able to know that, okay, since this has 3 columns, let me do broadcasting. Let me duplicate this B such that they are also, let me duplicate the value in this B 3 times such that you can actually do the multiplication. So that's the concept of broadcasting. So we can see the concept of broadcasting also coming to play in this particular piece of code, where this is a 3 by 3 and this is a 1 by 2. So broadcasting also works here. So if like for instance, if there is, so you can do the multiplication together. So for instance, if you mistakenly transpose the second matrix, like for instance, we had the mat 1, we had the mat 2. So, and it was the mat 2 that was multiplying the mat 1. So if mistakenly you transpose mat 2 and you actually do the multiplication, it's still going to work, but it will give you the wrong answer. But when named tensors come into play is that when you are defining a tensor, when you are actually defining it, you have to name it. So you say that you define this as a 3 by 3 such that the rows and the columns, they are 3 by 3. Also for this one that you want to multiply it with, you define the rows and you define the columns. So if you use this approach, you'll be able to do the multiplication. But if you mistakenly, by error, maybe you transpose this and you do the multiplication, it's going to give you an error simply because you performed name tensoring. So you named the tensor. So this name tensor helps to prevent wrong answers when you it helps to prevent wrong answers when you mistakenly do a transformation on a tensor that you are not supposed to do. Then I also talked about the concept of devices. So I've mentioned this quite a bit. So you have the CPU. Originally, it's the CPU that you send originally your tensors are sent to the CPU originally, but you can make use of the GPU. So if your computer has a GPU, this command here is going to change the location of the tensor from being stored in the CPU memory to the GPU. So what this line says is that device is equal to CUDA. So CUDA is the interface that enables us to use the GPU of our computer for deep learning tasks. Is that interface. So if the GPU is available, then you use the GPU, else then you can use the CPU. So all of these commands are to send the tensors to the GPU. That's if the GPU is available. So if the GPU is not available, then it will just use your CPU. Then we also have the TPU. So TPU stands for Tensor Processing Unit. So like I said, the TPU is far better than the GPU because the TPU is designed originally to work with deep learning models. So you have the TPU. So you have to specify before you can use that command, like I was saying, that to send it to a GPU, you have to change it to GPU. So if you change the runtime to a GPU, then you'll be able to use the I think maybe the GPU available on the cloud to run your tensors or to save your tensors. But the TPU is not available for free. Even if you change it, you will not be able to change it except you pay some money. So we will not be talking about the TPU because we can't access it for free on Google Colab. Then there's something called the metal device or the fake device. So the metal device is simply a kind of location where you are trying to store, you are creating like a fake or virtual memory, as it were, to store a tensor. So this is how you define a fake device or a fake location. So for instance, if you create this tensor, which is a 2x3, then when you try to view it, you will view that a tensor has been created, but it has no content because it is a fake memory. It's called the metal memory. Also, if you can create this large amount of tensor, which is like 100,000 by 100,000, using the fake device, which we call the metal device, and it will be created, but there is no content. So this touch.0 simply means that the matrix, all of it has zeros. But when we try to view it, we saw that the matrix indeed has been created, but then it has no content because it's a fake memory. Then we look at the if to say you didn't use this command, you didn't use this device equal to metal. If you just create the tensor, it's going to be stored in the CPU memory, and it's going to be stored in the CPU, and it's going to give an error because it is a large amount of tensor. So unless your computer has like up to 40 gigabytes of free RAM, then it won't give an error. So this was what I was trying to convey in that video. Then from here downwards, in the last class, I went over it again. So there's no point talking about it again. So that's just a summary of what I was trying to say in the video. So are there any questions? So if there are no questions, let's move to the lab. Who has been able to open this page? You've been able to open it. So how many people have opened it? 2. Okay, a few persons have been able to open it. So for those of you that are not able to open it, then just follow along, because just follow along with what we are going to be doing. So like I said, I put up the Google Colab. Then these are the things you need to do. So I will leave it's like an exercise which you have to submit. So like I said, you have to make these modifications to the notebook. So after making the modifications, you are going to submit the URL of the new Google Colab based on the modifications you did. You are going to submit it. Then you are going to submit also a video explaining your observations when you make these changes. So for the purpose of this class, you are just going to be looking at each of the blocks of code at a high level. Then we will be explaining it such that you might be able to do this instruction. So I left the quiz open. I will leave it open till maybe 3 days so that you will be able to do it. So let's look at, so it's about nonlinear regression. So the reason why it's nonlinear regression, we are going to be understand why it is nonlinear regression. So we are still working with the same AutoMPG data set that has 9 columns. So let me show you the data set. So this is the MPG data set. It has the 9 columns. So these are the 9 columns the data set has. So you have to load the data. That's the first step. So we've already talked about this previously. So these are the column names we are interested in. Then, so these are the column names. So I've already explained this. So I said you first shuffle it, then you divide it into training, validation, and test sets. So that's what we did here. Then we clean the data. So can somebody remind me, what's the cleaning of the data? What does it involve? So removing the missing values. So we try to remove the missing values. Then the pre-processing. So we are now at this step, pre-processing of the data. So I mentioned 2 forms of pre-processing. So, and those 2 forms, they have to do with the type of attributes that we have. So we call something continuous attribute, then discrete attribute. So we said for continuous attribute, you standardize. So standardization simply means x minus x bar divided by the standard deviation. So maybe this is your data set, so which is x. So you find the mean, that's x minus x bar. Then you subtract the mean from it. Then after that you find the standard deviation, then you divide by the standard deviation. So that's what we did for the continuous attributes. Then for the categorical attributes, we perform encoding, so embedded encoding. So I want to talk a little bit more about embedded encoding. So there are many types of encoding. So the one type of encoding I would like to tell you about is called the one-hot encoding. So it's called the one-hot encoding. So what's the one-hot encoding? One-hot encoding is used to convert categorical attributes into new columns. belong to them. So for instance, if you have this categorical attribute, let's say the country, let's say India, US, let's do Nigeria, and let's do Australia. So Australia. So why are these categorical attributes? Can somebody tell me why this would be categorical attributes? Okay, it is categorical attribute because it has 4 classes. So 1, 2, 3, 4. So I'm now talking about one hot encoding. One hot encoding. So in one hot encoding, what do you do? Because like I said earlier, deep learning models, they work with numeric values. They don't work with like character string. So what you are going to do now is to have this representation. Then based on this representation here, you have a 1 here, India, US, US, a 1, Nigeria, Nigeria, a 1, Australia, Australia, a 1. So the remaining columns are 0. The remaining columns are 0. So what have you done? In place of India, instead of India, it's going to be 1, 0, 0, 0. You've encoded it as 1, 0, 0, 0. So this is in terms of, in place of US, it's encoded as 1, 0, 0, 0. Then in place of Nigeria, Nigeria is encoded as 0, 0, 1, 0. Then of course, Australia is encoded as 0, 0, 0, 1. So that's called one-hot encoding. So that's a way you encode categorical. That's one way you encode categorical attributes. So instead of feeding this into your deep learning model, is actually these values that you are going to feed in as features into your deep learning models. So we use one-hot encoding. We use one-hot encoding when the features are nominal. So what do we mean by nominal? It means they don't have a structure. Nominal. It means they don't have any order. So there's no order to the attribute. Like, what's the relationship between these countries? Like, there's no really order. But in the case of when there is order in those categorical attributes, then instead of using one-hot encoding, we use ordinal encoder. So we use the ordinal encoder. So let me just describe the ordinal encoder. So the ordinal encoder is basically what I was trying to describe to you yesterday. But like for instance now, one of the categorical attributes we have in this particular data set. So the categorical attributes are year, so these are the cylinder, the model year, and the origin. So these are the categorical attributes we have. So can somebody, so I've listed this as the categorical attributes, which are also discrete, and then origin. So can somebody tell me, I will describe the second one, which is ordinal encoder. I will describe it shortly. But before I describe it, I've told you that one-hot encoding is used when the underlying features, there is no structure or there is no order, there is no fixed order. But if there is like a form of order, then you use ordinal encoding. So can somebody tell me, this cylinder, do you feel it to be one-hot encoding that one should use, or ordinal encoder? Yes, ordinal encoder. So it is correct, because the number of cylinders, of engine cylinders in a car, maybe it can be 3, 4, 5, 6, 7, 8. So I will know that the more the number of cylinders in a car, the more powerful the car is. So there is a form of order. So definitely we use ordinal encoding. So for this one here, which kind of encoding do you think we should use? Which kind of encoding do you think we should use for year? Okay, yes, ordinal encoding. Then origin. Okay, yes. Origin is the country of where the car was manufactured, I think. So originally, we can use 1/4, but in this particular notebook, we used ordinal. And the reason why we use ordinal is because for the origin, so this is the column for the origin. This is the column for the origin. So we just used 1, 2, and 3 to specify the country. So that's why we're using ordinal encoding. So in ordinal encoding, I would explain it shortly when we get to that part. So we are going to, so this is the function for the ordinal encoder. So this is like the main line that is actually doing the encoding. So we called, from scikit-learn, we called ordinal encoder, and this is the function that is actually doing the encoding of the categorical attributes. Then we need to build data sets or data pipe. So this piece of code here is just to build the data sets and to build the data pipe. So what are we actually doing here? So what we are doing here is that we need to have all of the features. So which are the attributes? So we have the features. So this is the raw data. So these are the features, and this is the target. So the target is the output. So we are just specifying where the features are going to be, where the target is going to be, then the kind of scalar, the kind of standardization or encoder you have to use. So building the dataset pipeline is all about specifying the input features, then the output, then the scalar. So this is what this block of code here is doing. So here we specified our continuous attributes as displacement, horsepower, weight, acceleration, our categorical attributes as cylinder and origin, then our output as the MPG. Then we just try to put each of our training, validation, and test sets into the dataset pipe that we have just developed. So this is the dataset class, and this dataset class is what we defined here, just putting some structure to the input, the output, and encoder. Then basically at the end, just defining it here. Then after that, we have to build in data loaders. So I've talked about these data loaders in the last class. So I said that you cannot just feed in the whole data at once into the model. You have to break it down into batches. So this is what we've done. So for the training data set is 32 batches. So it goes into the AI model in 32 rows, 32 rows, one at a time. So for the validation set, how many rows go into a batch? So also for the test set, so 16. So remember the equation I told you for the batch size. So the next thing now is the encoding. So this block of code here, the block of code here is just to define is just to implement ordinal encoding. So in ordinal encoding, so I was trying to explain it. So you have the unique values. So for instance, for the cylinder attribute, maybe it has these unique values. Then one method I told you yesterday is that you have to index. You have to index to the particular value of that attribute. Then another method, which is much more a deeper form of the ordinal encoder, is that you are going to define another matrix. You will define another matrix that would represent a particular number. So you remember here, we are defining a matrix kind of that represents the attributes. So we want to do the same thing. We'll define some set of values that will represent these particular features. And these are the features we feed into the AI model. So let me give an example. So this cylinder, so it turns out that this particular cylinder feature, it has three. Let me get the number of unique features it has. So the number of unique features it has okay, so these are the number of unique features it has. So 3, 4, 5, 6, and 8. So it has 5 unique features. 3, 4, 5, 6, and 8. So it has 5 unique features. So if you want to count it, it's 5 unique features. So what happens in ordinal encoding is that a matrix is defined, and that matrix that is defined, it gives like a representation of each of the values in the categorical attribute. So for instance, in place of a tree, it's going to generate, there's going to be some random, so the values that are being used to encode this, they are actually generated randomly. So probably it says minus 0.1, 2.3, minus 4.5. So for this row, this is like I said, they are generated randomly. So in place of this first one, these are the features that is going to be used as, that's the transformation. So you are kind of encoding this tree in form of these values. So maybe in the place of 4, you can just say maybe 2.5 minus 0.4, then 0.8. So in place of these 4, these are the values that are going to be used as features. So let me come again. So in the case of ordinal encoding, so you have the unique values. So you first of all get the unique values. So after getting the unique values, the ordinal encoder algorithm is going to randomly generate some features that is going to represent that particular value. So remember, in ordinal encoding is when there is a kind of structure to the data. So there is an underlying algorithm that we are not really going to talk about. So there is a form of randomness, and there is a form of algorithm that will ensure that the structure of each of the values are preserved. So it generates some random values that would represent the particular unique, the particular category or the particular categorical feature you are dealing with. So that's what the ordinal encoder, that's what it does. So here we are defining the dimension of that encoding we want. So for instance, the dimension of this is 5 by 3. So 5 meaning that 1, 2, 3, 4, 5. Then this 3 is left for you to determine this. 5 is already predetermined because it is the length of the unique values. But this 3 is left for you to put in the code. So for instance, for this particular case, this is 3 because we have 3 values that are representing this, 3 values that are representing this. So you can decide to put it as 4 or 5 or 6. So that is left for you to do. So this is where you specify the dimension. So here it was specified as 3, but you can decide to specify it as anything. So in the instruction, one of the things I told you to change is that probably you should change this to another number, then you should observe the results. So here we look at the embedding layer. So it turns out that, like I said, this cylinder has 5 unique values. That's why it is a 5 by 3. Then another categorical attribute is the origin. And the origin has 3 unique values. So definitely the encoder is 3 by 3. So that's the result that is displayed here. So this line of command here, the line of command here is just to view the categorical, the embedding. So like I said, it's just to view the first 5 embedding. So in place of the first one, 3. So these are the values that is generated. Like I said, some randomness and some order is involved in the algorithm. So for the second values, these are the values that were generated. So this is trying to show the first 5 values in the training set. So if you observe, this first one and the third one are the same thing, and they are the same thing is because they are pointing to the same unique value. Probably this one is a 3. So this one too, it means that this one too is a 3. It means that this one too is a 3. Then for the second set of tensor is for, so the first one is for the cylinder, then the second one is for the origin. So trying to encode the origin. So we can look at the encoding here. So you can see that this one here and this one, they are the same thing. So it means that they represent the same value. Then these two here, they represent the same value. So that's the encoding that we've done. Then it turns out that, like I said, for the encoding, you know that we had continuous attributes and we had discrete attributes. Can somebody tell me how many continuous attributes we are dealing with? So let me show you the code that specifies the continuous attributes. So this is the code that specifies the continuous attributes, and this is the code that specifies the discrete attribute or categorical attribute. So discrete attributes are also called categorical attributes. So how many continuous attributes are we dealing with? 4. How many discrete attributes are we dealing with? 2. Thank you very much. So the continuous attributes are 4 and the discrete attributes are 2. Please keep that in mind. But we did not put in the year. So when we first of all called the columns, please look at this carefully. Then when we first of all called the columns, the year was included, and I said that the year is a categorical attribute, but you can see that the year is missing. The year is missing when we were trying to define it, so it's completely absent. So one of the things I asked you to do is to add in the year column. So for those of you following, it's pretty straightforward. So you add in the year column. So that was one of the instructions I gave. Then you observe the result. So yeah, we're just using two of the discrete attributes. So one of the things I said. So how many of you are connected now? Are you able to run it? Who has been able to run some of it? Nobody is running it yet. Okay. So one of the things I asked you to do is to add the year attribute. So let's continue. So it turns out that, let's go back to this encoding now. Let me try to explain it once more. So it turns out that what we are trying to do here is that this, as a result of the ordinal encoder, all of these values, like this first tensor is for the cylinder. The second tensor is for what? Origin. So we are trying to display the first 5 values. Where do the first 5 values, where does it come from? The first 5 values came from here. So here. So what this code is saying is that you should display the first 5. So that's a 5 there. So you should display the first 5 values of the encoded form of the tensor. So you should display the first 5 values of the encoded form of the cylinder and the encoded form of the origin. So that's what it's saying now, which is displayed. So in other words, please listen carefully. This part is really very important. So remember that the cylinder was one attribute and the origin 1, letter 1, and the origin is the second attribute, right? But as a result of the encoding we've done, what we've done is that, because like I said, the cylinder has 5 unique values, but we decided that instead of using the unique values, we are going to represent it with like a vector or a column. So probably this one is for 3. I'm just saying, I'm not sure. Probably this is the encoding for 3. Probably this is the encoding for 4. So in place of just one value, we are representing it with 3 different values. Then also for the origin too, in place of just a single future, we are representing it with 3 futures. So please keep that in mind, because the cylinder itself is just a single attribute, but now we've broken it down into 3 attributes, into 3 futures because of all of this, and we specified that it's supposed to be 3 in that I've already described. So now we are going to build the model. So I want you to look at this slide carefully, so that to give a proper explanation of what I'm trying to say. So these are the continuous attributes. So how many continuous attributes did we have? 4. So this should be 4 in number. So this should be 4 in number. So for the categorical attributes, we had 2. This one is the cylinder and this one is the origin. So in place of this, after we did the pre-processing for the continuous, we did the standardization, it's still 4. But after we did the pre-processing, which is ordinal encoding, we changed this to 3. So from one future, this has been changed to 3 futures. Also for the origin, it is just a single future. We've changed it to 3 futures. So that means that the total futures that will fit to our AI model is 4 plus 3 plus 3, which is equal to 10. So that means that after doing all the pre-processing, instead of the 6, which is 4 plus 1 plus 1, it has now become 10 futures. So that's what this representation is all about. So after doing the pre-processing, then the futures are combined together. After combining the futures together, then you add your hidden layers, you put your activation layer, then of course your output layer, which is just a single layer, then you've built your AI model. So here is just all of this. What this diagram here is, this is the code that represents it. This is the code that represents it. So we add all of the futures. So yeah, all of the futures, all of the continuous attribute futures, that's what I highlighted. Then all of the ordinal encoder futures. So this is what I highlighted. So that's why I said 4 plus 6. So that's what is happening here. Then 20. Can somebody tell me what this 20 is? It's a random value we specified, but what it is actually? Can somebody try to tell me? Look at this line, nn.linear. I've mentioned this line of code before. I talked about it yesterday. nn.linear. Yeah. So this embedding, like I said, is 6. Then this is 4. So that means that 6 plus 4 is 10. So that means that you have 10 neurons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 neurons in the input layer. So if this one represents the input layer, what does this one represent? Yes, hidden layer. It's very correct, hidden layer. So it means that you specified 20 neurons in the hidden layer. Why can it not be the output layer? Yes, you just have only one output layer. You only have one neuron in the output layer. So it's just a neuron that is in the output layer. So that's why this line specifies that you have one neuron in the output layer. Then what this line is saying is that it's just a propagation of what you have here that you should put in here. So this will represent 20 and this represents 1. So there are 10 neurons in the input, 20 neurons in the hidden layer, then 1 neuron in the output layer. So one of the things I asked you to do is that you should add more hidden layers. That's one of the instructions I asked you to do. So here has only one hidden layer, but there are 20 neurons in that hidden layer. So what I'm asking you to do is that you should add more hidden layers. You can specify the number of neurons you want in each hidden layer. So the instruction is to add one more hidden layer. That's the instruction. Then of course training the data set. So then defining the loss function. So what loss function is he using? Yes, so one of the instructions I said is that you should change to another loss function. That was one of the instructions I gave. Then here is the optimizer. Can you tell me the optimizer that is being used? Adam. So one of the instructions I gave is that you should change to another optimizer. Then all of these are just, I think you can read it. Then this is the training loop itself. Now one of the things I didn't mention is that, yeah, we defined, because you can define the number of epochs that the AI model will run before it stops. But in this place, we implemented a piece of code that if the loss is not reducing, then after some time it should stop. So though we originally specified 100 epochs, but at 22 epochs, there was really no significant change in the training loss. So that's why the AI model and our program, which we pre-programmed it to stop at the 22nd epoch. Then this is a visualization of the training loss. Then this is the visualization of the prediction. So there's something that we introduced that I didn't talk of, and that is non-linear regression. So can somebody tell me, how do we change? What is the basic thing we introduced to move from linear regression to non-linear regression? Yes, we introduced activation function. So I want to show you where we actually introduced that non-linearity. So can you now, so this is the line of code that made it non-linear regression. So we introduced the ReLU activation function. So and that is what makes it non-linear. So let me go back to the instruction once more. So these are the instructions. So add the year attribute. So for those of you that they have internet access, it's just within 1 second you can do that. Change the embedding dimension to 4. So before, the embedding dimension was set to 3. Let me show you where it was set. So we set the embedding dimension. This is where we set it to 3. So I said change it to 4. So that one too is very, very straightforward. There's no big deal in that one. Then change to another activation function. So I showed you where we were using ReLU. Can somebody tell me another activation function? Sigmoid, tan, yes. So that's what I said. So in place of that place I said ReLU. So find another activation function and change it to it. So change to another optimizer. So the optimizer we were using was Adam. Then I said you should change to another one. Change to another loss function. So you were using the mean squared error. So I told you to change to another one. Then add one more hidden layer. So we only specified one hidden layer, which had 20 neurons. So I said add another one to the network. So is this something that you feel you can do based on the class of today? So just observe the results. We change. We have to do it. Yes. Yes. When you just observe, like tell me the changes. For the changes you can observe. You can tell me the changes in terms of the final prediction. Like here, this was our final prediction. So the target, the actual value, then the prediction, that's what our model is saying. So you can see that this is quite okay. Then you can also calculate, you can go further and calculate the loss itself, calculate the loss itself. Then, so it's just in terms of the loss and in terms of this graph that you just report your observations. So like I said, you would edit this logbook. So one of the things you can do is that, though I shared it with everybody, so anybody with the link can view, but cannot edit. So for you to edit, you have to save it in your own Google Drive. Then you're able to edit. Then you will send me that link of the edits you have been able to do. Then like a video reporting, you can, one of the things you can do is that you can just be changing it. You recording, do a screen recording session. You just try to explain the observations after making that change. Any question? Has anybody run any cell? Well, you have to start from the beginning. So one thing about Google Colab is that you have to start from the beginning. If you just start from a random cell, it's not going to work. It's just like a program. So it will start from the beginning. So for instance now, you start from the first cell. You start running from the first cell. So this cell is the first cell. You are importing the libraries. So this cell is really very important. If you don't run this cell, then all of the cells in your notebook wouldn't run. So anytime you start the notebook, you have to run the cells sequentially. Because for instance here, we define several variables that we are going to be using in the other cell. So if you don't run this cell, all of these variables is not seen, is not recognized by it. So it's not going to work. Then another thing is that if you want to, there's a way you can run. Run all means run all the old cells from beginning to the end. So you will not start running it one by one. So you can use the run all command to just start from beginning and to the end. Then the run before is just to run anything before that particular cell. Then run is just to run the focus cell. So run cell and below. Just run the cell you are in, then everything below. So that's how you can run it. Any other questions? Yes, sometimes the result is not going to be displayed. Like for instance, if you run this particular one, there's no result that is going to be displayed. The only time in Python, like this one too, this cell, there's not going to be any result that will be displayed. Even this one, anytime you want to see a result, you have to call a particular variable name. Like in this case now, we called this variable name. That is when you see the results. So in Python, if you just define a variable and assign in values, you wouldn't see any results. If you want to see a result, then just write the variable name in another cell. That is when you can see the results. So that's the structure and that's the syntax of Python. So for instance now, if you change this to 4, you wouldn't see any results. It's probably at the end of that graph that you now see the result when you eventually. So what I would advise is that maybe when you change this to 4, you saw what? Okay, yes. So you said you saw it here. So if you change this to 4, here we change to 4 and here we change to 4. So then that's because we called the variable name here. Yes, exactly. You also see the change. So she told me another place where you see the change too. So you also see the change here. So before you just have 3 columns, but because you change it to 4, then you would have 4 columns. So those are the observations that I want you to make. Any other question? So please try to do this assignment. It's very important. So if you do this assignment, this class exercise is supposed to be an exercise, but our time is up. So, and the internet, some people say that the internet is not good. So that's why we are not being able to do it. So please, I will leave the window open till 5 p.m. tomorrow. So you can submit till 5 p.m. tomorrow. So I will leave it. I left it open till 5 p.m. tomorrow. So any other questions? And you are screen recording, but yes, you can just be screen recording the notebook, then just be making some audio talking. Then in that first assignment I gave you, some of you didn't submit the video. It was just a presentation you submitted. Some of you, about half of you. So like I said, all of those assessments is continuous. It's not just your test I will use. Probably the test will just be 5%. So all these assignments, they are adding up to your continuous assessment. So for those of you that need to be working, and I specifically said video, people just gave a presentation. So your marks is also reducing in terms of the continuous assessment. I said it's a video I watched. That's the instruction. Video. But some of you is just no, I'm not showing your face. Just a presentation, no video. It was just a PowerPoint presentation, no video at all. Okay, there's a recording. There's audio inside. That's not what I said. That's not what I said. I said it's a video. MP4, a video. It's not